So I'm very pleased to introduce Dimitar Sasselov, who we tried to schedule to come and actually visit us, but he's another one of the people for whom doing a remote talk is actually much easier. So it's a positive part of COVID-19 that we get a talk from Dimitar. I should say Dimitar originally from Bulgaria. His main Canada connection is he did his PhD at the University of Toronto. For the last 20 some years, he's been at Harvard, where he is now the Phillips Professor of Astronomy and the Director of the Origins of Life Initiative. He was also a member of the MOUST satellite team with PI Jamie Matthews, who's here. So he visited Vancouver and UBC many times in the past. He was heavily involved in the Kepler mission. He's essentially trained as a theorist working on radiative transfer in atmospheres and so on. A few years ago, decided to kind of change direction, and knowing more about what planetary atmospheres might be like, to try to do laboratory work on the origin of life. So that's what he's going to talk to us about today. So it's all yours, Dimitar.
Thank you, Douglas, and thank you all for having me. I really appreciate that. I'm still planning to come and visit when things open up. So I really want to visit with you guys. So anyway, so yes, I'm still a theorist. In fact, half my work is still theory, and my theory students are working fine through the lockdown. So we've had no problem with that. But with the lab, we just started, and I want to tell you a little bit about it because it's very exciting. We hope that in the next couple of years, we'll have some very new and interesting results to report. However, even today, I have some new and interesting results to report about the topic, which is how does stellar UV light help or participate in the origins of the building blocks of life. And the first question, of course, is that must be happening in the prebiotic period. And we have to understand the stellar UV light as well as the environment in the prebiotic time, the prebiotic planet, whether it's early Earth or any other exoplanet that we'll call prebiotic. This is not a good picture because it has already growing stromatolites, meaning that's not prebiotic anymore. But basically the idea there is that you need a planet which is rocky with some amount of water. The Earth is like that. An ocean worth of water is really a small amount of water. Many of the planets that we discover out there probably have a lot more volatiles, and that leads to dilution and the concentration of many of the chemicals, the main elements and atoms that we need for the molecules, the building blocks of life as we know it, cannot be concentrated under those conditions. So the rocky planets with a little bit of water, you need the water, but you also really need to avoid it being too much. So what is prebiotic chemistry? I want to kind of tell you about some of the basic assumptions and also to define what I will keep referring to as prebiotic chemistry. So first of all, I really want to stress here that right now, the project we're working on is for life as we know it. That is really the origin of life on Earth, the building blocks for the molecular inventory of life as we know it on Earth. And we understand that it will be geochemical conditions, which are the root of that prebiotic chemistry. And you will see that you really need to have those last for a while. In particular, it is useful to think of life's origins as two phases, which are not necessarily separated from each other, but have a different nature. The first phase I call the deterministic phase, and it is really the actual chemical synthesis of the molecules which we call building blocks. And it is deterministic, we believe, because, well, you'll see why. There is very narrow pathways which lead to those blocks. It is not anything goes, or vice versa. You don't have the complications of Darwinian evolution, in which, if you rewind the movie, Stephen Jay Gould used to say, and you play it again, it will come out somewhere different. But there is the transition to phase 2, and this is when contingency turns on. So in other words, you have to consider those two phases as playing together and interleaving with each other. And phase 2, if you want to be more specific about this, is when the large polymers, which are the genetic molecules, today's life, that's RNA and DNA, and peptides, which are the proteins or the protoproteins, small ones maybe to begin with, exceed a certain length. And that length is, mathematically, people have worked on that, Eigen in particular, is not that dramatically large, 200 bases or so on. And then suddenly exploration of sequence space can no longer be exhaustive. So you get onto path of contingency and Darwinian evolution. So these two phases together is what I would refer to prebiotic chemistry. In particularly phase 1. Phase 1 is the prebiotic chemistry which leads to the protocells. Sometimes the people would think and even talk about the protocells as being the next stage, the Darwinian stage. But it is not exactly a good way to position them in phase 1 and phase 2 that way, because those first cells will have, we believe, a functioning genetic molecule, which also has feedback mechanisms to improve itself. That is, it can copy without any help, without enzymes, it can copy itself, but also has a feedback with some of the properties of the membranes of the cells, or some of its own copying properties to lead to different populations, and some of those populations will compete with the others and will be better and so on. So Darwinian evolution with genetic molecules, maybe the exact genetic molecules we have in life today, like RNA, could work that way, but with one very important difference. Every cell, every living thing today is capable of building its own building blocks, synthesizing its own monomers for the polymers which make it up. These protocells will not have that ability initially. In fact, you have to evolve to that point. And even conservative estimates is it takes hundreds of thousands of years to get to that point. So phase 1, which is the deterministic phase of simply chemically synthesizing all the necessary building blocks, will have to continue uninterrupted throughout this whole period of the protocells essentially learning how to make them themselves. So in other words, the protocells will have to live off the land until they figure out how to make their building blocks, which is the case of microbes today, of course. So that is why I want you to understand the extent of our project. So we want to reach in the lab the ability to build these protocells by feeding them with phase 1, that is with chemistry, prebiotic chemistry that produces those building blocks in a way in which they can absorb them, they can use them, and they can evolve the mechanisms to make them. The only way in which this can be accomplished is by building it in the lab. It's a very large system in terms of combinatorics. It cannot be modeled in a computer at this point. And so one of the goals of about 4 or 5 labs that we are working on this at this moment is to build a functioning chemical protocell, which then will allow us as a toy model in the lab to study the development of this self-sustained system that is capable of Darwinian evolution, which is then really the beginning of a living biosphere of actual microbes. Self-sustained is very important here. So before you have self-sustained real biology, you have to have a prebiotic chemistry to provide those monomers. And those monomers, in the case of genetic molecule, as many of you know, of course, the individual nucleotides, which polymerize in a very specific way with a backbone made of phosphate. There's the piece, the phosphorus here. There is a little cartoon here. Phosphate and ribose sugar. And to the ribose sugar, you attach 4 very specific molecules, which are called nucleobases, and which are essentially the alphabet when it comes to the genetic code, the AGCP of DNA or the AGCU of RNA. And in this case, you see C and U here, the smaller cyclic bases, and the bicycle bases, the purines, as they called, adenine and guanine. So basically, the development of this prebiotic chemistry, which I'm going to describe in some detail for you right now, and which depends critically on UV light from the sun or from any star, is based on answering that question. How do molecules like RNA come to be in a chemical fashion? We know how they do, how they synthesize by life today, and it is done in a very complicated way with the help of very sophisticated proteins, which are called enzymes, and it has nothing to do with the origin of life. It's just 4 billion years of evolution. But when a chemist looks at this monomer, the nucleotide, it naturally falls into 3 pieces: a nucleobase, a ribose sugar, and phosphate. And for many years, for 50 years, people would synthesize those pieces, the individual parts, particularly the ribose sugar and the bases, and would try to essentially stick them together. And that doesn't work. This is a well-known problem for more than 50 years now. It works under special conditions. We, of course, can do it industrially, but it doesn't work under natural conditions in any way in which you could say this is how it happened in the beginning. So as an alternative, the 3 scientists that you see down there, Towner, Gerland, and Sutherland, in John Sutherland's lab in England, proposed a completely different way of synthesizing those monomers. And that happened 11 years ago, and now 11 years later, with the help of a couple of more labs, but back with John Sutherland and Matt Towner, this has become a whole network, and let me call it a new prebiotic chemistry paradigm, where UV light is central. I almost have drawn it here like the heliocentric model with a UV light in the center of the universe, with some feedstock molecules, like of course water, but particularly hydrogen cyanide. And then that network, as of today, is capable of reproducing most of the nucleotides. There are 5 of them for RNA and DNA. 1 of the lipids, or 2 precursors of the lipids, and 12 of the amino acids. You know, life uses 20. So 12, this network can do 12. Is this enough to build a protocell? The answer is yes. So if that project is finished tomorrow, and I would say it's not, but if it's finished tomorrow, then the next step, building the protocell, is very close at hand. So the question is, what is this new prebiotic chemistry developed by the Sutherland lab and now with a few other labs, including mine, involved in this? Well, UV light is central, and it is central in jump-starting the process. The jump-starting of that synthesis is by producing what they call hydrated electrons. It turns out that in water, and of course all of the prebiotic chemistry works essentially in water, as not surprising. Life as we know it relates to that in many ways. Water is the solvent. So you put ferrocyanide, this is denoted here as Fe2. You put ferrocyanide in water together with some amount of sulfate. Bisulfate is particularly here. And you irradiate it with UV light of particular wavelength. We'll talk about that in a moment. And you photodetach electrons, which thermoize in the water. And for a period of nanoseconds to a microsecond, actually are in the water as individual charges surrounded by water molecules. That's what is referred to as hydrated electrons. Is one of the most potent and valuable reducing agents from a chemistry point of view. So this is the first step in that process. It can be either run through this cycle of cycling ferrocyanide to ferricyanide with the chaperone molecules of bisulfate, which essentially is sulfur dioxide dissolved in natural water, or a copper cyanide cycle, which works similarly, but doesn't need the bisulfate necessarily. Or both cycles can work together. In fact, copper cyanide and ferrocyanide at certain natural planetary conditions can coexist. And there is no problem if they both provide those hydrated electrons. So those hydrated electrons produced in this case from the ferrocyanide in the picture at the bottom would affect the hydrogen cyanide in the water. And you could have a lot of hydrogen cyanide in natural water in the early anoxic Earth because you will have cyanide salts like sodium cyanide in a lake in which you also have ferrocyanide. So ferrocyanide and hydrogen cyanide come hand in hand. So what happens with the hydrogen cyanide, it actually undergoes what's called the reductive homologation. The reducting agent, of course, is the hydrated electron. Homologation chemists call the addition of carbon-carbon bonds or carbon-nitrogen units. So you essentially start with HCN and then you put two HCNs together and you have a molecule that grows that way. So very quickly, with the help of oxygen from the water, you end up with simple sugars and some amino acid precursors. It only takes 7 steps, in fact, and this is fairly easy to do in the lab. When I say that, that's usually the bar for that is Dimitar's bar, which means that even I can do it. And if I can do something, that means it's robust chemistry, one that can happen on its own on any planet that has the conditions. So this is very easy to do. Now, it's very easy to do if you use the right UV light. The right UV light means the right flux and wavelength window. And the wavelength windows is very specific. You need UVC light from 200 to about 300 nanometers in terms of energies that between 4 and 6 electron volts. And we now understand why, and you will see it's not only to produce those hydrated electrons, but it has many other roles as well. So you know where UVC light is? Well, there is UVB, UVA, visible and infrared. Of course, UVC is all the way at the bottom. So 200 to about 300 is what people call UVC. And of course, today, UVC light is blocked by ozone. The ozone layer blocks it to the surface of the Earth. But before there was oxygen in the atmosphere, and particularly ozone, it was not blocked. Most stars, like the sun or M-dwarfs, produce some of it. Maybe M-dwarfs don't quite get the right amount of flux. That's still a matter of exploration in the lab, and we'll see where this goes. But the sun definitely gets you enough in terms of flux. And up until we did some of these experiments, people were not using or didn't even bother to use the right amount of flux or the right wavelength dependence as you would get from the sun and with the cutoff for water and the atmosphere of the early Earth. They would just use mercury lamps, which have a single emission line right here at 250 nanometers right here. And the chemistry worked. But now we know that they were lucky because the chemistry actually has a wavelength dependence as well as a flux dependence, but particularly wavelength dependence. And just most of it turns out worked for the chemists if they baked their samples with mercury lamps at 254 nanometers. If you really go to the levels and the fluxes and the wavelength dependence which we expect the sun had at the time, then it also works, but only because you added some of the higher energy UV light at about 5-6 electron volts at 220 and 230 nanometers in particular. So what are the cutoffs? Well, the cutoffs are due to water, and it's kind of obvious. If the chemistry needs water in order to happen, and water shields you from UV light below 200 nanometers, then that's what your cutoff is. In addition, turns out that the CO2, carbon dioxide in the Earth's atmosphere, at a wide range of values, which we expect were valid for the early Earth. Here we use the model specific to 3.9 gigayears. That's because people had built it very carefully. Nowadays, we have done this for a different range of expected abundances in the atmosphere of the early Earth. Before or after 3.9 years, you always get this same cutoff at about 200, 210 nanometers. So this harsher, higher energy UV light, which is below 200 nanometers, is always blocked, which by the way is a good thing because that's when you start producing OH minus radicals from photolysis and of the water itself. And those radicals really destroy most of the organic chemistry that we call prebiotic chemistry. And of course, above 300 nanometers, it's always available even today. The ozone blocks it, blocks the UVC today, but not above 300. But it turns out that the UV light, UVB light is less important for our story here. And so, so the question was, is this, how does this connect to other planets if we want to search for prebiotic planets beyond understanding the early Earth? Mars, of course, but also exoplanets. And basically the big question there is CO2 always present? Are there any other gases that can block UVC light? And that should depend on the general oxidation state of the mantle. So we did some models there in order to assure ourselves that the scaling between 1 Earth mass and 5 Earth mass for bigger planets will still work out. And it seems so far that this is the case, but as I will mention at the very end, this is one of the actual situations which is funny. You have many textbooks, I would say all textbooks that I've seen would tell you that rocky planets end up with mildly reducing nitrogen-dominated CO2 atmospheres. But it's based on a number of assumptions which have never been really tested directly. And this is an opportunity for exoplanet research. And I'm kind of trying to lobby a group of exoplaneteers that we actually do some of those tests in the coming future with JWST. So to summarize this, UVC light is what we need for the chemistry, and I'll show you why. That's my next topic. Why exactly UVC light? Why this energy range? UVC light is what we need, and we are fairly sure that it will reach the surface of prebiotic Earth, and including shallow lakes in which you may have the hydrogen cyanide and the ferrocyanide and the copper cyanide, which will jumpstart the process that will lead to the building blocks, and which works in the lab. So we think it's very robust, and as long as this works, and as long as you have the right amount of flux, it's always important, UVC flux, which depends mostly on the host star, and you have the right wavelength range, which is UVC, which depends mostly on the atmosphere and what is in the water, but mostly on the atmosphere, then you're fine. And then let me tell you why UVC light and what are its roles. 3 roles. The first one is obvious. I already mentioned it many times. UV-driven synthesis. So basically, the UVC light is the source of energy. You know, a lot of people say, well, what's the source of energy for your origin of life? Well, it's the UV light. Although I have to say that a certain amount of energy, chemical energy, is stored in hydrogen cyanide. The CN triple bond is a very specific source of energy. But the main source of energy is the UVC light. It has to be UVC light for those hydrated electrons to be produced in the right amount. But what I learned as I got myself deeper and deeper into this in the last few years is that while this is important and necessary, I mean, you can't even start the synthesis without it, probably the most important thing about the origin of life is actually number 2, and number 3 is kind of the same as number 2, but at a higher level. Number 2 is that the UVC light also cleans up chemistry with the source of energy, and whatever source of energy you give it, produces a lot of products. Organic chemistry is known to produce a lot of products. So what organic chemists do in their labs is purify. They purify that, they purify this to get pure products. Well, on the early Earth, there is no chemist to purify stuff. So what happens if you don't purify things? Well, your yields go down, but more important, you can't get function. Why? Because you get a mess. You get these isomers of the same building block that is going to end up in your RNA, but they're slightly different. And you get a polymer, which is a helter-skelter chain of things, which then fold badly or not at all, and certainly will not have proper function. And by proper function, I mean, for example, copy themselves. We know that for a fact, actually, and people have known it since, the 50s of last century. But what is a new realization now is that UVC light is capable of not just providing the source of energy for synthesis, but also the source of energy for cleaning up, or as you call it, chemical selection. Now, the UV-induced self-repair is actually the same conceptually process, but now applied to polymers. So when we are not talking about individual small molecules like the monomers, when you have polymers, UV light can induce lesions, as they call it in modern life, or defects, damage the polymers. And only those polymers and those forms of polymers that have the opportunity to self-repair with the help of more UV photons, so now you're talking about multi-photon processes, transition from survival to biological function. It's extremely interesting. It is a new line of work, which only started, I would say, about 2 years ago. And so I don't have enough results or time to describe it to you, but it's similar to number 2, to the UV-driven selection. If you're interested, I will be happy to talk more about it in the question and answer period afterwards. So just as an outline, the UV-driven synthesis is the first thing I want to show you. And that has to do with photostability of the building blocks and the feedstock molecules, the molecules like hydrogen cyanide and ferrocyanide, from which you actually start the process and feed the process, build the molecules. The UV-driven selection is about selectivity, obviously, and I think is the most important aspect of it. And finally, the star and its planet, because UVC light plays so many different roles, influence the selection of which components would be there for life to originate from. And so if that is indeed the case, then as astronomers or physicists, we can say, well, wait a minute, if that's true, then we should be able to find evidence for that selectivity or for that selection. And this is, in fact, the big project which I'm pressing on with right now. So let's start with the synthesis. In fact, it's difficult to just start with the synthesis, which is this sequence here. You know, UVC light produces hydrated electrons, homologation, and simple sugars. I would add to this the selection, because you will see that you can't separate one from the other. As soon as you start this process, and this simple diagram at the bottom here is already 7 steps of its own, you have to start worrying about high yields and function, even at that level, high yields and function. And so hence about selection or cleaning up, producing just the right molecules, not just everything. So I've been talking about this prebiotic chemistry, and it looks a little bit like this. This is kind of the current network in a simplified way, of course. Most of the reactions are shown, but not all of them. They all start from this area here, which is from HCN. It is not shown here, the ferrocyanide, the bisulfate, which produce the hydrated electrons and then cycle themselves and produce more hydrated electrons. That is completely skipped. So this is a very simplified network, as you see here. But basically gives you an opportunity to see that from hydrogen cyanide, you produce formaldehyde with a pair of hydrated electrons. With another pair of hydrated electrons, either after this step, you produce the first 2-carbon sugar, this molecule here, glycoaldehyde it's called. And then with another pair of hydrated electrons and continuous homologation of more and more hydrogen cyanide, of course, you end up with this molecule here in the center, which is the 3-carbon sugar, 3 carbons in the vertices here, which is glyceraldehyde. And now with glyceraldehyde and the molecule called 2-amino-oxazole, this interesting little thing here, you go along this line and end up with the nucleotides for RNA. Remember, I was telling you that people had trouble producing ribose sugar. Ribose sugar is this pentagram in the middle here, and connecting it to bases, which can be synthesized separately, independently. But notice that in this synthesis, which was pioneered by John Sadowan, you kind of bypass producing the ribose sugar directly. You produce something else, which ends up being a ribose sugar with a base. Very, very smart way to do this. The more important thing here, smart or not, is that this goes very quickly at very high yield. You produce those 2 nucleotides in essentially 50-50% yield, which is amazing in any chemistry lab. And this is the kind of chemistry which I told you even I can do. So in other words, it's very robust. You change the conditions a little bit here and there, and it still makes a nucleotide. So if you have a lake, in other words, which can get you those initial feedstocks and you have the right amount of UVC light, you end up with these nucleotides, whether you want it or not. So they will accumulate in that little lake. These other parts we are not going to explore, but basically those green squares are different amino acids. I told you 12 of them. And here the orange, yellow-orange ones end up with lipids. Lipids are the molecules which produce the membranes that I showed you from Jack Shostak's lab in the second view graph at the very beginning. So the big question here is, here we use the UVC light for the synthesis. So there are all these steps, all the way to the glyceraldehyde, you need this UVC light to keep producing hydrated electrons to reduce the hydrogen cyanide. Once you get to this point, you start producing too many isomers, like for example here. And the big question here is who cleans up? And as you see, there is a little bit of UV light here, noted. The UVC light does the cleaning up. And so you start with synthesis and very quickly you end up with selectivity in order to finish with high yields of those monomers. And not only high yields, but only the right ones, because if you get the isomers, you will not be able to polymerize a functioning polymer, RNA in other words. Now, I want to show you how this works. That is why and how this selectivity works. And in order to show you that, unfortunately, I have to say something which to those of you who have taken chemistry is obvious, but to me it was a revelation. So I got used to these stick diagrams in which you see the molecules, and yes, they are in water, so you account for the fact that water molecules are waiting around, and when you need the hydrogen atom or oxygen atom, the water with its properties is there to help or not help, whatever. But you know, I personally had forgotten or didn't know that whenever I consider the properties of any of these molecules, you cannot think about them in isolation unless you're in interstellar space. If you're in water, the water molecules that surround them, the first shell for sure of water molecules that surround those molecules, is always arranged in particular ways. In fact, there are several permutations, but N is really a small number. There is a small set of permutations in which these water molecules can be arranged. And they always arrange that way, and that really affects the photodynamics, the photochemistry of those molecules. In fact, it affects all their chemical properties when they're in water. And that is very important to our story here. And it is important because the question is, what happens to these molecules? And here you see bases, of course, C and A from AGCT, adenine and cytosine. But the question is, what happens to these molecules under UVC light? And it is a good question because for many years, and to some extent even today, a lot of people would say, oh, UV light destroys our organic building blocks of life, so you have to hide from it, especially UVC light. Well, not really, and especially not the ones which are used by life today. That, I have to say, was pioneered about 10 years ago, 10, 15 years ago, by people who studied the nucleobases themselves. They looked at the nucleobases in water, that's very important. And they noticed that the excited state lifetimes under UV radiation of the, what they call the canonical nucleobases, the one used by life, AGCT and U, are much shorter, and I mean orders of magnitude shorter than those of their derivatives. And by derivatives, we mean, and that's for people like me, there is an example with uracil and thiamine, U and T, you know, the canonical ones, to some of the derivatives or isomers or similar molecules to uracil. So to chemists, these are very similar because under normal chemical reactions, you would make a lot of those, okay? So that actually happens quite often. But if you irradiate them, these ones survive because they have very short-lived excited states. And this why these ones here, the derivatives or the isomers are dead because they really cannot get rid of that energy. And so you all know what happens in molecules when you excite UV pump in the Franck-Condon region. You go to, say, another singlet excited state, S1, Maybe you stay there, maybe you can pass a barrier and go to a triplet state. If you stay in the singlet state, after a while, nanoseconds or more, you will fluoresce down back to the ground state. If you end up in a triplet state, you'll stay even longer and phosphoresce. This is radiative deactivation. And those long-lived excited states that I'm showing to you for some of those derivatives, they would fluoresce and phosphoresce if they even manage to get to that. Most of them will be destroyed. So the question is there a shortcut to this? It turns out that occasionally, very rarely, there is a shortcut. Non-radiative deactivation. The non-radiative deactivation happens through something which is called a conical intersection. So you go on, you pump to S1, and somehow, miraculously, the ground state and the singlet excited state actually intersect somewhere in the landscape of the diagram. And you very quickly go back down to the ground state by vibrationally cooling yourself with respect to the water. So what are these conical intersections? These conical intersections are actually a fairly newly discovered phenomenon. It was suggested for the first time in 29 by von Neumann and Wigner, of all people, on mathematical grounds, just around the time when Born and Oppenheimer had written their paper, the famous Born-Oppenheimer approximation, of course, which, just to remind you, says that the nuclei, the atoms in a molecule, are heavy and are completely decoupled in their motions from the electrons, which bind those atoms. So you can, from a computational point of view, you can do the computation separately, but from a conceptual point of view, what the electron does and what the atoms do are two different worlds and two different things. Well, conical intersections are when the Born-Oppenheimer approximation actually breaks down. It doesn't happen very often, and Edward Teller, after von Neumann and Wigner suggested that, said, well, if it does happen, it will lead to very ultra-fast relaxation down, and we won't see it because it will happen so fast that we won't see fluorescence or phosphorescence. But since then, and until about 20 years ago, literally until the end of the 20th century, the opinion in the community, apparently, was that conical intersections can happen mathematically, but do not happen in real life. That is, there are no molecules which have the symmetry to produce those kind of degeneracies, and where you would actually have a conical intersection. Until 20 years ago, when people actually tried experiments on ozone, which is a triple molecule of 3 oxygens with particular symmetry, and managed to find one. So it's very rare, the conical intersection, but it's a very, special thing, because that means that this particular molecule, by doing things like puckering here or moving things up and down, would actually get rid of a lot of energy, produced in this case by interaction with the UVC photon, very easily and quickly, and hence it will not be photodamaged. So in other words, molecules like that are very photostable, and it's very sensitive on molecular structure. It really can make a big difference if you change the molecular structure even a little bit from a chemistry point of view. You know, from me as an astronomer, when I look at that, well, yeah, that's a big change, but the chemist will say, oh, that's not a big change from a chemistry point of view. So there is kind of the first step in this big question. Can we find evidence that there was prebiotic chemical evolution due to UVC light? And a diagram like that for the basis canonical versus modified bases, which are produced by normal chemical reactions, shows you that maybe you can answer that question, because the excited state lifetimes of the canonical ones are orders of magnitude lower than most of the modified ones. And by the way, the hypoxanthine here and this one turned out to be mistakes in the measurements. We have remeasured them since this paper published that, and they actually in this domain here. The problem, however, with this is not the end of the story, because this is just for bases. And as I explained to you with the prebiotic chemistry, the new prebiotic chemistry paradigm, you don't go through the synthesis of bases at all. You go directly to nucleotides. And so the big question is, when you do the monomers, the nucleotides, do you still get that UV-driven selection advantage from UVC light? And the answer is you do. So one last thing before I show you how we do this is I want to tell you what is this whole thing about the high yields. Why do we care about the high yields? As you saw already from the picture with the network, large network, you don't get to the final products in 1, 2, or 3 steps, or multiple steps, more than 10 typically, but of the order of 10 to 15 steps in each case. If you have at every step a fairly low yield, you end up dead in the water, because generally speaking, it goes as the yield, average yield, to the power of the number of linear steps. And whether it's linear or convergent, if you have many steps and you have yields that are of the order of 50%, you end up nowhere. This in synthetic chemistry is referred to as the arithmetic demon. And you have to fight the arithmetic demon. And the only way you do is by making sure your yields are high, as you can see here. And you do that in the lab by purifying and by doing all kinds of tricks, but Mother Nature has to do it naturally. And this one example of the first 7 steps that I was telling you, Paul Rimmer did that just to illustrate how the flux, which produces the solvated hydrated electrons, can really kill you in 7 steps. If you have the right amount of yields for each of the 7 steps, you end up with micromolar to millimolar concentrations, which is just the right thing. That's what you want. It's perfect. But if you start losing on the yields and go close to 50, 40%, you essentially dead. 10 to the minus 15 molar, obviously nothing is going to happen there. So that's what I mean by high yields. And more on the case of selectivity, you really need to produce just the right monomers. You cannot produce a whole bunch of others. This is the problem with sugar products. If you do it the way Stanley Miller did it in the Miller-Urey experiment, yes, you get the right sugars that you need. There they are with the red arrows, but you get a whole bunch of others. It's a big mess. So yes, this was a very exciting experiment back then, and you do get those amino acids and ribose, but you get so much other stuff which you cannot take out. I mean, it takes a very well-equipped lab to actually extract the necessary amino acids and ribose from those experiments. In a natural environment, who is going to do this? So basically, this is the problem. And if you remember these last steps of the production or the synthesis of the nucleotides, I told you that the UVC light cleans up. This is what I mean. If you look at this lower part here, it says byproducts and other products. You see here? Byproducts and other products. And if let me magnify it here. Byproducts and other products. So you get the right molecule, which eventually will lead to your nucleotides. But you get exactly 16 other products, 16 other ones, like the ones I showed you. Fortunately, they are all photo-destructive by the fact that these guys have conical intersections. These other guys, they isomers and derivatives don't. So this is the bottom line here. And by the way, it takes 3 days of baking. When we use the right UVC light with wavelength dependence, it happens much faster. So the wavelength dependence really matters. We did that, it worked, and it was great. And you can see that is when you have to do this C to U conversion, it really depends what wavelengths you're using. As the experiment shows you, really between 260 and 280. And if you're not there, you're not going to get it. And this is because the arithmetic demon will kill you. So how do I do it? That's kind of, I'm ending the talk to show you how we actually do this. The previous was sound the results from this. Well, this is the laser equipment before we add all the other stuff. There is now, this whole thing is full of stuff. But this big box at the bottom there is the femtosecond laser. So it's a laser which produces femtosecond laser pulse. It's off the shelf, you can buy it. It's nowadays, a lot of companies make them. This other big box here is the spectrometer. So that's where we get the spectrum. So the really unique and custom-made part of this whole apparatus are these 2 boxes here. Set of crystals, a lot of crystals, BBO crystals, which convert the red light, 800 nanometers of the pulse laser here, into UV light without destroying the pulses. The pulses are still femtosecond pulses, but now I can simulate the stellar UVC light here. I can go anywhere from 200, from 190 nanometers to 350 nanometers by tuning it using those crystals and pumping that light into the spectrometer. And in the spectrometer, I get the pump, which is the UV light, which excites the molecules and the chemical reactions which are here in the sample folder. And simultaneously from the same laser, because they have to be timed very precisely to femtosecond precision, I get what is called the probe. So it's called the pump probe technique. So the probe goes through a delay line, and then itself is transformed from a monochromatic red light, 800 nanometers, to white light, right here, to white light, and goes through the sample right after the pump has arrived. So basically the pump pumps and the probe probes. And the probe probes not just once, but multiple times. You move the delay line, and as the absorbance versus time diagram shows you here, you get, if it's decaying, you get the photodynamics or the chemical dynamics of the molecule with its spectrum, of course. You see an absorption or emission spectrum, usually absorption spectrum, and you see it as a function of time over a period of time. These spectra look like this. So here the top is actually a 3D picture. In the direction up, the y-axis is actually time in femtoseconds and picoseconds. In the x-axis at the very bottom is wavelength. So that's in nanometers, from 318 to 540 in this particular case. That's one of the spectra I took, and that's why it's so noisy, but I've gotten better since then. And this is particularly the spectrum at 39, let's say 40 picoseconds, about here, so right here. So you can see the different values, but you can see the spectral lines. They're broad, relatively broad spectral lines. There are actually 3 of them here, one here, and one there, of this particular molecule, which is one of the precursor bases, inosine, it's called, 8-thioinosine with sulfur. Remember, it's a cyanosulfidic chemistry, so sulfur is involved. And so that's what we do. We actually pump and probe, and we get these spectra and see how long they stay in the excited states and in which excited state. And this particular one has a conical intersection. So all the excited states disappear within picoseconds, not nanoseconds and microseconds, but picoseconds. And basically, you see here, the decay is very clear. how the decay quickly goes almost to 0, and that's particularly for the spectral line, which shows this sulfur atom moving out of the plane. If you have puckering, which is another conical intersection, you have a different photodynamics, but again, works pretty well. So I like to call my laser system a universe in a box, because the range of time which you span between photoactivation and deactivation, especially when you don't have a conical intersection, if you measure this in terms of years, you can see it's more or less 10 to the 10, same range of time here that we cover. So did UV sculpt the molecular inventory? Well, we are screening now about 200 isomers and byproducts, and I'll tell you in a year where we stand with this. And then the oligomers is what I told you, the self-repair of them. So to finish this, in summary, I think the star and its planet could influence directly the selections of life's components. And that is because there are this really interesting quantum mechanical, physical, chemical, conical intersections, hyperlines in some molecules, but not in others. And if we manage to actually show this in the lab, I think it will be really a smoking gun, telling you that there is something to this, that life on Earth, at least, as we know it, with the molecules, the basic molecules that we see today, was affected by UVC light and essentially was sculpted by it. So that's the story I wanted to tell you, and obviously it's not a finished story, so I hope to come back in 2 years and tell you more about it. Thank you.